Look up at the night sky. For millennia, humans have gazed at those pinpricks of light, weaving myths about their origins. Today, we have a different, more profound story to tell, not of gods, but of geometry, quantum whispers, and an expansion that shapes everything we see. This is the story of our universe's evolution, a narrative that begins not with a simple bang in the void, but with a profound transformation of space and time itself. The most pervasive image of our cosmic origin is that of a colossal explosion in empty space, flinging galaxies outward like shrapnel. This picture, however, is deeply misleading. A better analogy is to imagine a vast, infinite loaf of raisin bread baking in an oven. Each raisin is a galaxy. As the dough rises uniformly, every raisin moves away from every other. There is no center to the expansion. No raisin is special. The very fabric of the dough space itself is stretching, creating more room between all points. This is the essence of cosmic expansion. Galaxies are not simply flying through space. The space between them is growing. This revolutionary idea found its evidence in the early 20th century. Astronomers like Edwin Hubble, peering through powerful telescopes, discovered that distant galaxies were fleeing from us. The telltale sign was in their light, which was stretched to longer, redder wavelengths, a redshift akin to the lowering pitch of a departing train whistle. Crucially, the farther away a galaxy was, the greater its redshift, and therefore the faster it appeared to recede. Plotting this relationship revealed a linear law. Velocity is proportional to distance. The slope of this line, now called the Hubble Constant, gives us the universe's expansion rate. Run this cosmic film backward in your mind. Galaxies converge, the universe becomes denser, hotter, and more extreme. Extrapolating all the way back, we arrive at a state of unimaginable density and temperature roughly 13.8 billion years ago, a phase we call the hot Big Bang. Notice the careful phrasing, a phase, not necessarily the beginning. This hot, dense state is as far back as our classical equations can confidently take us, but it may not be the ultimate origin. The framework that allows us to understand this expansion is Einstein's general theory of relativity. In this view, gravity is not a mysterious force reaching across emptiness. Instead, mass and energy tell space-time how to curve, and this curved geometry tells matter how to move. Picture a stretched rubber sheet. Place a heavy bowling ball in the center. It creates a depression. A marble rolled nearby will curve inward, not because of a direct pull, but because it is following the contour of the warped sheet. On a cosmic scale, the collective mass of the universe dictates the curvature and dynamics of all space-time. When mathematicians like Alexander Friedman applied Einstein's equations to a uniform universe, they found dynamic solutions. The cosmos could naturally expand or contract. For a time, some, including Einstein himself, favored a static, eternal universe. But Hubble's observations shattered that notion. The universe was undeniably stretching. This led to a grand cosmological debate in the mid-20th century. On one side was the hot Big Bang model, championed by George Gamow and others. It predicted a primordial furnace where the first light elements were forged and, crucially, that a faint afterglow of this heat should still permeate the cosmos. On the other side stood the steady-state theory, proposing an eternal universe where new matter continuously appears to maintain a constant density as space expands. Nature delivered its verdict in 1965. Arno Penzias and Robert Wilson, two radio astronomers troubleshooting a persistent omnidirectional hiss in their antenna, had accidentally stumbled upon the cosmic microwave background. This was the cooled and diluted remnant glow of the hot Big Bang's fiery plasma, a nearly uniform bath of radiation bathing the entire sky. Its discovery was the knockout punch for the steady-state theory and solidified the hot Big Bang as the dominant paradigm. We were literally seeing the echo of the universe's early hot phase. Yet, this triumphant model exposed deeper puzzles. The was incredibly uniform, but not perfectly so. Tiny millionth of a degree fluctuations were later mapped, revealing the seeds from which galaxies would eventually grow under gravity's pull. Furthermore, the second law of thermodynamics presents a profound mystery. Entropy, or disorder, always increases. An egg scrambles, but never unscrambles. This defines time's arrow. Yet, The early universe was in a state of remarkably low entropy, highly ordered and smooth. Why did the universe start in such a special, organized state? Pushing our equations back toward time zero leads to a crisis, a singularity. Density and curvature become infinite, and our laws of physics break down entirely. This is the mathematical hallmark of the classical Big Bang. However, most physicists see this not as a physical reality, but as a signal that classical relativity must yield to quantum mechanics. At the incredibly tiny Planck scale, spacetime itself is thought to become a seething, probabilistic foam, where notions of a smooth continuum and a definite beginning may no longer apply. This insight has spawned breathtaking ideas about what could have preceded or precipitated the hot Big Bang phase. One leading concept is cosmic inflation. This proposes that a fraction of a second after the putative singularity, the universe underwent a brief, exponential expansion, driven by a repulsive energy inherent to space itself. This inflationary surge would have ironed out wrinkles, explaining the CMB's uniformity, and stretched microscopic quantum fluctuations to cosmic scales, planting the seeds for galaxies. It elegantly solves several major puzzles and sets the stage for the traditional hot Big Bang expansion we observe thereafter. Looking even further back into the realm of quantum gravity, ideas become more speculative but no less fascinating. Perhaps our universe emerged from a quantum fluctuation in a primordial void. Or maybe it is one cycle in an eternal series of expansions and contractions, a big bounce, where a prior universe collapsed to a hot, dense state before rebounding into our own. Some theories, like the no-boundary proposal by Hartle and Hawking, suggest time itself loses its meaning at the earliest moments, with the universe having no distinct initial edge or moment of creation, much like the North Pole on a globe has no point further north. This is where the true wonder lies. We have pieced together a robust, evidence-backed history from a fraction of a second after something all the way to the present cosmic web of galaxies, stars, and planets. The hot Big Bang describes that evolution masterfully. But the ultimate question of origin, what, if anything, came before that hot, dense state remains an open frontier. It is a question that merges the cosmic with the quantum, gravity with uncertainty, and pushes the human intellect to its limits. We are privileged to live in an era where we can probe these mysteries. The CMB is our most ancient artifact, a baby picture of the cosmos. Future observations of gravitational waves from the universe's first moments, or deeper studies of the large-scale structure, may one day provide clues about inflation or even earlier phases. The journey is not about finding a final, comforting answer of a definitive beginning. It is about the relentless, thrilling pursuit of understanding. Every answer unveils deeper questions, and in that cycle of doubt and wonder, we truly connect with the vast, ancient, and magnificent universe we call home.